Okay, everybody, welcome to our ITC class for, it is October 11th. This is our intro course, and we're going to be talking today about Chapter 3, which is all about network protocols and communications. This is one of the sections that I really talk about being one of the main concepts that are important inside of this intro course. The big ones are this, what the Osi model is, what the TCP model is, how IP addresses work, both IPv4 and IPv6, as we'll see later in the chapter. And then the basic communication that you can do configuring router and switches. Today we're going to talk about network protocols and communications. This entire chapter is based upon the concept of protocols or communication. The easiest way to think about a protocol is simply a language. When two people talk to one another, we obviously have a message we want to send. Meet me at the store. Are you at home? We have to some way send that message. It has to go across some media or medium, just like I talked about in Chapter 1 for looking at the different things a network has to have in order to be a network. And then the receiver has to be able to take that message and in some way decode it and then understand it. So what we're going to see is we're going to see the messages being encoded into some protocol or some standard, and then we're going to send it across some medium or media, and then we're going to decode it, and it will then be read on the opposite end or the receiving end. The other item that we will have is looking at these, and obviously what they do here is they just show you a little thing. I've got an idea, I send it across, and the idea has to be received on the opposite side. Same thing happens on a computer. We just go across this particular instance, and we encode the message, send it across, and decode it on the opposite side. Now, when we look at rules, we already know all about rules. So if I look at you and we're having a conversation and I go, huh? You know I am asking you a question. You know that I don't understand what you just said, or I have some type of question because of the rising inflection of my voice. That is a rule. It's in human language, almost all human languages other than Chinese, is what I've been told. A rising inflection is a question. Just like we can't really understand this, human communication between governed rules is very difficult because it doesn't follow the structure of the English language, but we can translate it, and if we use the grammatical rules that are associated with the English language, we then can understand it. Protocols between computers are exactly the same. It deals with taking the message and encoding the message. So taking your request to go to a web page, encoding that request in some form or fashion, formatting it, and then encapsulating it. And that message encapsulation is going to be set by a message size, and there's going to be limits on message size. You've probably heard of a term. How many of you have heard of the following term? I got to get my notepad up because I always use notepad. You know that. How many of you have heard of the term MTU? What does that stand for? Anybody know what MTU stands for?
Maximum transmission unit.
Yep, maximum transmission unit. So it's the largest size packet frame piece of data that can go across a particular media or medium. Typically with Ethernet, it's around 1514 if we're not using jumbo frames. So that's the typical size for Ethernet. I've seen it listed at 1504, 1514 roughly in there. But this is non-jumbo frame, okay? And the reason I say non-jumbo frame is because we have a method now, and especially within the data center itself, to use bigger packets or bigger frames. We use jumbo frames, and those frames can be huge. I mean, about 90, I think it's 9186 or something, it's 9,000 bytes, but it may be even bigger depending on your data center. But this maximum transmission unit is based upon the type of protocol you're using. We also have message timing, how messages are sent and received, and how long you're going to wait before you try to retransmit. Are you even going to retransmit? That's going to be a protocol question when we look at TCP versus UDP as protocols. And then our options, that could be connection-oriented, connectionless. All of those are different types of ways to deliver a message. When we look at message encoding, I've kind of already talked about this, but we take an idea and we're trying to discuss or describe a sunset to someone. How do we do that? What do we do in order to send that message so that the opposite side can understand it? For computers, it's pretty easy. We're just going to encode the digital information, the information into some type of form and send it across. The important thing is that both sides are speaking the same language. In this picture, if this person was speaking French and this person was speaking English and they did not know how to speak the same languages, there's no way you could describe the sunset to someone. Likewise, two computers, one speaking TCP IP, one speaking Apple Talk, they will not be able to talk to each other. So again, for you and for your students, the easiest way to describe protocols is say that a protocol is a language. Okay? So that you can understand how that language is used between the two different devices. Inside of our protocols, we have message formatting and encapsulation. We already have an example of this that we use when we send letters, if anybody actually sends physical letters anymore. But we actually put in a recipient. So we're going to say, okay, first off, we've got the data. This is the data that's placed inside this envelope. The envelope is addressed, okay? And in this, we're going to say who the destination address is. So here's our destination address. The sender's address. And then we're going to do the started message indicator, which is the dir. The recipient destination, and then the content, which would be the actual letter itself, and the source identifier, and then what we call an end-of-frame delimiter, or the end of the message. Now, it's a little bit hokey to look at it like this, but this is encapsulation. It's the exact same thing we've done with a physical letter. Computers do this a little bit differently. They have frame addressing, which we're going to learn. These are called MAC addresses. These are physical layer addresses that are burned into the network interface card of the computer's NIC. The other items in here that's data will be upper layer protocol information that's being carried as data. And then this end of frame, when we talk about actual Ethernet, which we'll talk about in a next chapter, the actual end of frame will be what's called a frame checksum, or a CRC, which is simply a mathematical calculation that's run against the frame when it's sent and then run again when it's received, to ensure that the frame is not damaged or modified in transit. Message size, when we look at the message size, if it's too big, it will be discarded by the receiving end. So we just have to make sure the message sizes are the same on both sides. And timing's the same thing. One of the things we're going to talk a lot about is access methods. And if you've done any basic networking, excuse me, over the years, you will be fairly, probably know some of these. They're fairly well known. Let's imagine, here's one that's pretty easy, and it's called token passing. Now this is an older one, and in token passing, there's a little token that is sent around the ring, and if you have the token, you can send data. I call this the Lord of Flies access method, because it's just like in Lord of Flies. If you were holding the conch in the story, you were able to talk. See, I had to use that in English major for something. That's all it's good for. But if you can actually hold the conch, you can talk. Same thing with token passing. Now, the neat thing about token passing, it is a non-contention based. In other words, there's no way for there to be collisions, or there should never be a way for there to be collisions, because the host that has the conch is the only one that can talk. So the host that has the token is the only one that can talk. Now, token passing used to be part of what's called token ring. It's gone away. We still have FIDI. We have some other things that could be used. But our more common methods now are contention-based methods. And these methods are associated with Ethernet. And one is Csma CD, which is carrier sense multiple access with collision detection. And the way this works, and we'll talk more about it in the next chapters too, but I want to go ahead and introduce it here, is the devices listen on the media or medium, and they say, is it clear? In other words, they perform a carrier sense. If it is clear, they can send. Now, the multiple access means that two devices could possibly listen and see the line clear at the same time and could send at the same time. If they did, a collision would occur. If that occurred, the very first machine to see that sends what's called a jam signal. It sees the collision and says, here, there's been a collision, and then everyone performs what's known as the back-off algorithm, and then will randomly try to resend their data. The bad thing about a contention-based access method is that if it's not configured correctly, and now in our real-world examples of how we're doing Ethernet now, it's fully switched networks, micro-segmented networks, really should not be any collisions, but it's still using CSMA CD, and that would be there could possibly be collisions within an Ethernet network. Another one we use is CSMA CA. The only difference is it's collision avoidance. That's used in 802.11 wireless LANs, where you've got a signal that's sent before the device actually transmits to say, hey, I'm going to send something. Then it sends it. But it's still an access method. It's how you put information onto the media or medium, and that's all the access method is. Any questions about those two? They're really just two access methods, because CSMA, CA, and CD are very similar. No questions? Okay. Flow control and response timeout will also be part of these two items with our message timing. Flow control will be what we call window sizes inside of TCP. How much information can you send before you need to receive an acknowledgement? Also, flow control will be, hey, I'm being overwhelmed, slow down. And you can actually send a message to say, slow down the data transfer. These three items are very important, and they are the three different ways that messages can be delivered. And they are unicast, which means, and I'm just going to use it with the computers. Unicast is one-to-one, so it's from one source to one destination. Multicast is from one source to some, and that is to a group, to a subset. All right. Multicast are those addresses starting with 224.0.0 or I'm trying to remember IPv6 FF08, I think. I'd have to look that up. That's escaping me at the moment. But there is a multicast series of addresses in IPv6. And then broadcast is one to everyone. One of the things I teach my students, broadcasts are bad. Now, does that mean we can do away with all broadcasts on our networks? No, it does not. There's no way to completely do away with broadcasts. But we try to limit the broadcast as much as we can on a network. So unicast, one-to-one. Multicast, one to some. And broadcast, one to all. Okay? And then here again we have our rules. Common language. How are we going to change this information into frames, which are layer 2 items we'll talk about? And then how is that information going to be put across the line? Is it going to be light pulses? Is a pulse of light a 1 or a 0? All of that are your physical layer rules of the protocol suite. Now, here's things kind of neat. When we talk about a protocol suite, and then we talk about a protocol suites are groups of protocols working together, we can't spell, to perform host-to-host communication. And we're going to talk about the TCP IP protocol suite. And you will see all the different protocols that are part of this suite. We're also going to learn about the fact that the TCP IP suite was originally broken into these 4 layers: application, transport, internet, and then the network access layer. Or a good way to remember it is at N, or if you need a 10. That's a kind of a little mnemonic for you to be able to remember. But each one of the protocols in the suite work at one of these layers. And we'll show you that in just a minute. But it's just a group of protocols working together. For instance, you probably all are extremely familiar with HTTP, right? HTTP is an application layer protocol that works inside, okay, Keith says, Nita, that's a good one too. I hadn't thought about that. That's excellent. You could also, that's very good. NITA, that's very good. That's bottom up. So network access, internet, transport, application. That's better than mine. Excellent. I'll start using that one because Nita's easier to remember than AT10. See, learn something every day. But the HTTP protocol is an access layer. At transport layer, we've got two. We've got TCP, which is reliable, and his unreliable little brother, who is UDP. And the internet layer, our main protocol, is IP. And then one of the very neat things about the TCP IP suite is there are no protocols defined at the network access layer, which was the best idea that they came up with, because by not defining physical and data link protocols, they made it where TCP IP can run on anything. It can run on token ring. It can run on 10 megabit Ethernet. It can run on gigabit Ethernet. It can run on, fiber, anything. The beauty of it, and that is one of the reasons TCP IP has taken over, is because it can run on anything. Nita, good, I'm got that. So here we're looking at network protocols, looking at how we can, at layer 3, and we'll learn what layer 3 is here in a minute, how those protocols can be used to move information around a network. And it's using the header, so we can look at paths for protocols. And again, all of this is pretty much exactly what we've already gone over. So let's move on forward to look at interaction. And here they are. The application layer, transport, internet, and network access. Down here at the network access layer, we're using Ethernet, but that's not actually defined by the TCP IP protocol suite. IP, which is our network or internet layer protocol, which is connectionless, by the way, and also logical addressing. And then TCP at layer, up at transport layer. And this layer, which is layer 4 of the Osi model, is then providing services to this, the application layer. Each one of these layers is providing services to the layer above it and receiving services from the layer below it. And that's true of the Osi model too. This is one of the models we will learn that is a protocol model. So this is exactly how the protocol works versus the Osi model, which is a reference model, which is a theoretical model. So here's some more of our protocols and different standards. So TCP IP, you see here are application layer protocols. Some of them you're very familiar with. Transport layer protocols, the internet layer protocols, IPv4 and v6. And then down here, network access protocols. Here's our old IPX-SPX. Those of you who had to suffer through Novell NetWare. And if you ever had to actually use AppleTalk, I feel for you too. But there are different standards, open standards. All of these are open standards that are available. Well, TCP IP is an open standard. Novell, technically, and AppleTalk are not open standards. But ISO and TCP IP are open standards. So how long has TCP IP been around? A long time. Okay. So basically, in 1969, the first message was transmitted. I was about, let's see, a couple months old when this happened. So it's been around a long time. I think something that surprises people, I believe, where's it at? 95, yeah. The IPv6 standard has been around since 1995, and we still don't use it. So you're looking at 20 years. Well, yeah, 20 years, roughly. But it's getting there, and it's one of the reasons we're really having to use IPv6 Day was on 2011. We're really having to learn to use it because we're so far out of IPv4 addresses, it's not even funny. So here are some of the different protocols again. It's good for you to learn these, to know which ones are application layer protocols, which ones are transport, which ones are internet, and then the network access layer, so that you can identify these on a test. Make sure that's available for you. Are there any questions about any of these? I like the way that, Chip, go ahead. Anybody? The only thing I would argue with this a little bit is I don't technically know if that is an internet layer protocol. I understand what they're saying, but you know, it's kind of this. I don't know. It's especially the IGRP. It's got its own transport layer protocol, so it's a little weird. And even OSPF, it runs on top of the others. So I understand why they're saying it is, and that's probably the correct place, and that's where most people say it would be. But that's the only thing that I would kind of raise an eyebrow at a little bit. Now, here's an example of actual encapsulation. So a piece of data, in this case a web page, is placed as data inside a frame. So this data, this is user data. It gets a TCP header. It gets an IP header, an IP address. Then it gets an Ethernet header. And then it gets a CRC at the end because it's a frame if it's Ethernet. And it gets sent across as ones and zeros. Now, one of the things I like to do here is I like to kind of just give you a quick overview of what's in these sections. So when you look, the TCP header, that's going to be a protocol and a port. For instance, in the case of a sent message to go to as far as a source TCP port and protocol, if you were going to a web page, it would be, the protocol would be TCP, and the source port would be some random number above 1024. So let's just say 3000. The destination port would be TCP 80 because you're going to a website. The IP address, there would be a source IP, and there would be a destination IP address. And these would be, depending on, it could be 192, I'm just going to put down a V4 address, 192.168.12.10 or whatever, that's the source. The Ethernet header is going to be a source, and I'm going to put this the way it's in the frame, a destination MAC and a source MAC. Now I'm going to do something real quick to show you how you can find your MAC address on your machine. If you've got a command prompt and you type ipconfig/all, and you don't have 47 different virtual NICs, you can actually look for your physical address. And right here's the physical address of my machine, 02004C 4F 4F 50. Now here's a neat thing you can do too. Because the MAC address, and we'll actually go over this later, but the MAC address is made up of different see if I can actually find it here. Let me go back. I can find it at Wireshark, I believe. There it is. I can put in the first portion of my MAC address. First 24 bits are the OUI, which is the organizational unique identifier, and then the last 24 bits are the serial number. So for me, 02004C, find it. Find it. Okay, let me put, I didn't put it in there correctly. Colon. Now let's see if we can find it. No maxes. I'm going to try this again. Maybe I put it in wrong. 02 dash. Man, I cannot type today. Oh, I'm just going to look back at that. Hold on a second. There it is. 90 dash B1 B1 dash 1C. Now, Bill, you can tell because my MAC address begins with 90, and sorry about that, I showed you the wrong one. This is my actual MAC address down here, the physical MAC address, 90B11C. Since I did that, you can see that my computer is a Dell, has at least a Dell NIC, or that NIC is registered to Dell. That's how we can keep up with source and destination MAC addresses. That's one of the parts of the source and destination MAC address. Now, I described to my students that this is kind of like the Russian doll thing. You know, you got the data, you put that inside a little Russian doll, you close that up, encapsulate it, and you put that in another one, then you put that in another one. And then on the opposite end, once it's received, it gets decoded. So on the opposite end, it's looked at, and they've got this backwards, but it's looked at and then it's decoded so that you can see, is this my MAC address? If it is, it passes it up. Is this my IP address? If it is, pass it up. and then it can eventually pass it on up into the application layer to the program that needs to deal with it. In this case, it's a web browser receiving data from web server. And I had it backwards, but same difference. Any questions? Hey, Sandela. So when we look at standards, here are some of our standards organizations. The IEEE, which we can go look at, IETF, INA, TIA. All of these are different places that make protocol standards and just standards in general. And here we look at some of the ones. We have the Internet Society, the IAB, and we've got the Internet Engineering Steering Group, and then on forward. And we've got INA and ICANN, which are responsible for handing out IP addresses. And ICANN is based in the U.S. and hands those out, and so does INA. So it's those two. They're doing a much better job of handing out IP addresses for IPv6 than they were IPv4 because they were so willy-nilly in the beginning because they didn't expect the internet to grow to the size that it is today. Here are some of the working groups. 802.1 is the higher layer LAN. 802.3, you've heard of those Ethernet standards. 802.11 are wireless standards. I like this 802.15, it's wireless personal area networks. Kind of interesting. We mentioned personal area networks 2 chapters ago in chapter 1. And then on forward, now we're getting into smart grid items and regional area networks. So different groups that are working to develop the standards that come out. One of the things that's always been interesting is how, and it's slowed down a little bit, but how the 802.11 standards there for the longest time, the actual ratification of the standards were way behind the implementation of the devices, or actually the hardware you could buy. You could get pre-standard 802.11a or 802.11b or 802.11b, well, actually 802.11g, 802.11n, 802.11ac. Okay, that's a very good, another good one, Kishi. I'm learning all kinds of stuff today. Get MAC shows you the MAC addresses of the different devices on here. The only thing that's kind of weird is because it's got multiple, it doesn't tell me what it's associated with, so you'd have to know that some of these are virtual adapters associated with, I have both VMware Workstation and VirtualBox installed on this machine, so that's a very good one. Get MAC. If you only had one MAC address, then you would be able to easily see what that is. Like I said, I've got so many that it's a little harder for me to see. Okay. That's very good, though. Thank you. You see, I don't teach teach some of the OS classes anymore. Probably need to go back and do that. This is a really neat way of looking at the two different models side by side. The OSI model, which is a reference model, okay? And here's how I like to describe reference models versus protocol models. I used to, and I know people don't do this anymore, but years ago I used to build models, and I used to build, airplane models, and my favorite models were F-16s, okay? So if you look, I'm going to go out here and I'm just going to do a real quick. Hasegawa, who is an extremely good model maker. They make great models, okay? You can see a 1/72nd scale model of an F-16, all right? Now, you look at this and you see, you think about this Block 50, which is one of the earlier models come out, but you look at them and you say, okay, if I put together a plastic model of an F-16, how many pieces do you think even a great model kit would have? Anybody? Any idea? Maybe 200. I mean, that would be, and that's a phenomenal model. It'd be 200 pieces, 300 maybe at most. How many pieces does a real F-16 have if you tried to put one together? Thousands, millions, yeah. It could be, Simon, good point. I mean, it could be, like I said, For a model, a regular model, 250 pieces would be an amazingly detailed model. For a real F16, 250 pieces wouldn't even put probably the wheel struts together. So, a reference model is like a plastic model of an airplane or a car. It has most of the parts, but it doesn't have it down to the level of detail that will let you actually perform real communication on a network. A protocol model has been divided the way that it truly works in the real world. In other words, we're going to learn what the application, presentation, and session layers do, or what they're supposed to do in the OSI model. But in the real world, all those functions are really performed in one grouping in the application layer of the TCP/IP model. So HTTP, DNS, DHCP, and FTP, they're all application layer protocols that perform some function associated with these top three layers of the OSI model. The transport layer, you'll see there's a one-to-one match. Transport layer on the OSI model, it performs the same function as the transport layer on the TCP/IP model. And two protocols there are TCP, which we're going to learn is a connection-oriented guaranteed delivery protocol, and then UDP, which is a connectionless non-guaranteed delivery protocol. It's the unreliable brother of TCP. The network layer is the same as, performs the same functions as the internet layer, and there's our protocols, and then data link and physical perform the same as the network access. But now I know they're putting down here PVP, frame relay, and Ethernet. These really are not TCP/IP protocols. They're open standards that TCP can run on. So for a reference model, it's a basic model, consistency, something we can use to describe the basic communication process between two hosts. A protocol model is how that's actually working, how two hosts actually communicate with each other. So all people seem to need data processing. You need a mnemonic to remember this. So all people seem to need data processing. If you want layer 7 to layer 1, all people seem to need data processing. That's layer 7 to 1. If you want the one from layer 1 to 7, which I like better, please do not throw sausage pizza away. That's layer 1 to layer 7. This is a model, a reference model for how two devices communicate or two hosts communicate. So the application layer contains protocols used for process-to-process communications. In other words, it provides support to applications that rest above the application layer. The presentation layer is responsible for converting information into any intermediary formats that it needs. This is also where compression or encryption would take place if it's taking place. The session layer establishes, maintains, and terminates dialogues between two hosts. Transport layer is used to segment, transfer, and reassemble data between two end devices. The network layer is designed for, first off, it's logical addresses, and it's used for the exchange of information between networks. Again, logical addresses as a network layer. The data link layer is where we do framing. It's where we encapsulate into frames, creating frames over a common media or medium. Also, the data link layer, we do have error checking at the data link layer. Now, we do have error checking at the transport layer too, but we have error checking at the data link layer, and that's our CRC. We'll talk much more about it as we move forward. And then the physical layer, I always call this the blue-collar worker of the internet world or the computing world, because the physical layer, it just converts things into ones and zeros using the correct function for the media or medium you're connected to. I always tell people, one of the things about the OSI model or any model, each layer receives services from the layer below it. Obviously, the physical layer can't get anything from below it, and then provide services to the layer above it. However, this particular setup, one of the things you need to kind of remember is when you're actually dealing with these models, okay? The application layer talks directly to the application layer. The presentation layer talks to presentation. They do not realize what's going on below them. That is why when I say there's error checking at the transport layer and there's error checking at the data link layer, there's two different types of error checking, okay? The data link layer is doing a CRC. The transport layer will be doing segmentation and reassembly. So you can have the same function at two different layers. It's just two different types of error checking. So again, application layer, same functions as the first three layers of the OSI model. Transport is the same as transport. Internet, same as network. Network access is the physical and data link layers. Okay. All right. Message segmentation. This is taking a large message and breaking it into smaller pieces. One of the reasons we do this is so that one message will not hog all the bandwidth. We also do this so that if you have a message destroyed or damaged in transit, that message does not have to be resent completely. You can just resend a smaller segment. Multiplexing is taking communications from two different devices and then making sure they're on the line, but when they get to the opposite side, that they are associated with the correct session. Down the road, you'll hear things like flows, flow control, net flow, all those types of things where you can look at how flows are reassembled. So here you see how the pieces are labeled for easy direction and reassembly at the other end for segmentation and multiplexing. Very important to remember these PDUs. At the physical layer, the PDU is a bit. It is just a 1 or a 0. At the data link layer, it is a frame. At the network layer or the internet layer, it is a packet. At the transport layer, it's a segment, and then above that is considered data. Okay? Bits, frames, packets, segments, and data. And sometimes you'll see bits, frames, datagrams, segments, and data. But just, I learned it the way I've got it here. Bits, frames, packets, segments. We've already looked at an encapsulation example, so I'm going to skip this one. I'm going to skip that. Now, network addresses or layer 3 addresses, we're going to talk about those. We have several different types of addresses that we've talked about already. One is the physical address, which is that burned-in MAC address on a NIC. Network addresses are logical addresses. In other words, there's no reason that my PC has the IP address it has other than the fact that our network admins decided our building was going to be this block of addresses, and my IP address would be on this VLAN, and then my IP address comes from that. It could be any other IP address, but that's how it was decided. My MAC address, though, is determined by Dell because it's a Dell computer. So that's how I get that. Now, source and destination IP addresses, those will be used for your communication. So here we can see there's a source IP and there's a destination IP. And that's how we're going to learn that information is routed across routers, is using the IP of the destination and then returned by the source IP. Data link addresses are those addresses that are local. Now, one of the things that's important to notice here is notice how at each hop on a router, the layer 2 addressing information changes. In other words, the destination NIC, in this case, if we're sending all the way to a remote host, we're going to learn about a thing called proxy ARP. This router will tell this sending host that the NIC MAC address is actually its MAC address. So the destination NIC address will be this router, and the source will be this sending computer. And then when it goes to this next, the router de-encapsulates the packet, or the frame, de-encapsulates it up to layer 3, and then re-encapsulates it with whatever media is on this. This could be HDLC instead of Ethernet. And so the layer 2 header information changes every single jump. Now, layer 3 doesn't necessarily change. It can, as we learn about NAT down the road, but we won't learn about that for a while, okay? But that's what they're talking about here, is how the data link addresses change, the layer 3 addresses do not change pretty much by default, okay? Now, like I said, we'll talk about NAT down the road, and you'll learn about that. Here's an example of communicating with a device on your same network. We're going to learn that what happens before you can communicate is you'll check your local MAC address table. If you don't have an ARP entry for the destination IP address, you will send out what's called an ARP request and say who has this IP address and what's your MAC address. That server will send back an ARP reply, and you'll see the destination MAC address then becomes that local MAC address, and the source MAC is your source MAC, and then your source and destination IP. Now, the reason the destination MAC goes first is for speed. Every single device that sees this has to look at least up to layer 2 to determine if it's its MAC address. In this case, that speeds things up, especially in the old days before we had switches and microsegmentation. It would speed up the process greatly. But this is on the same network. You'll see it's got the local device's MAC address. If it's on a remote network, it's a little different. When you send out an ARP request, that's a broadcast. That broadcast can't pass all the way across all these routers because by default we're going to learn that routers stop broadcast. So instead of this web server replying with its MAC address, this local router, which is the default gateway of this PC, will respond with a proxy ARP and say, hey, I see what you're trying to do. You're trying to get a MAC address on a remote host. Well, you're not going to be able to do that. So just use my MAC address, send it to me. I'll figure out how to get it there. And then it will be sent over to the default gateway, and then the default gateway can figure out how to route it using layer 3 routing information across this network. Does that make sense? Any questions about that? Because that is a very important concept. Okay. As long as it's clear, I just want to make sure. And folks, that's it. That is chapter 3. Now, one thing I'm going to tell you about the labs, this Wireshark Lab, you're going to be able to do a little bit of it inside of the lab on NetLabs, but Wireshark's also a great thing just to install on your local machine and play with it. Be careful, though, because it is a sniffer. Make sure you have the ability to do that. Don't go sniffing traffic you shouldn't sniff, because it is a packet capture software that sometimes you can get in trouble for using it. All right. Folks, that's the end of chapter 3. I'm going to stop the recording.